Welcome back. We are into the 9th module, and with this module we will begin talking about the physical layer. We have already had set the tone for the physical layer. We have already looked at the types of signals and all that. In this particular module, we will be looking at how physical layer transmits the bits across and the challenges and the issues with that thing. Okay. It does data communication. In fact, the biggest advantage of having a physical layer is that it carries the bit across, and there is no physical layer, there is no network. Okay. So, it limits the functionality of other layers. For example, if I use an Ethernet card maximum data that it can send in a given frame is only 1500 bytes for historic reasons. So, a transport layer segment maximum amount of data that it can carry must be less than, in fact, if you calculate normally an IP header is 20 byte and TCP header is 25. So, 1460 bytes is the limit that you have for the transport layer TCP. You can't have a bigger segment than that if you are using an Ethernet card. Okay. So, even wired or wireless case also, you have lot of limitations coming in once you start using a typical physical layer. In case of a wireless physical layer, the other problem comes in. In a wireless physical layer, the problem is that there is a lot of noise in air, and it limits it does so much of error that it is always better you should keep a shorter frame. When you keep a shorter frame, it affects your data link layer and it affects the other layers as well. So, point is physical layer drives many things of other layers. Okay. So, it decides in fact lot of things, error handling and amount of data to be transmitted, and format of a frame also is, you may be surprised, format of a frame, the upper layer, how it requires. For example, if you use a wired physical layer like Ethernet, the amount of error that you get is very less. So, you do not require a lot of error handling kind of fields in that frame. In fact, there is no error handling frame except the field called CRC. We will be learning about that. In case of a wireless, a lot of additional things are to be kept because of that. Okay. So, physical layer actually have an impact on frame structure as well, and it also have the effect on speed of transmission. If you have a better physical layer, you have for example, a fiber optic cable, you will have a much better transmission rate. If you are using a copper cable, you will not have the amount of transmission rate that you probably have with the other the fiber optic cable. Okay. And wired and wireless, you need different strategies actually to manage, and we will soon see, but let me give you a hint. Wireless normally introduce lot of errors, and wired usually the amount of cables that the type of cables that we use today does not involve much of the errors. So, the entire design is based on, like in case of wireless, you stress a lot on handling errors. In wired case, you just forego it in most cases. Okay. Basically the duties, we will start with the duties of physical layer. What exactly a physical layer should do? The physical layer, in short, should send bits across from sender to receiver, but the bit will not be sent as it is. So, it will be that needs to be converted into signals and then sent across. Okay. So, some form of signals, digital or analog, okay, and send them to the other. The receiver does what? It collects these waves and convert them back to bits, okay, and once they convert that back to bits, it will pass it up to data link layer to decide what to do further. But then it is critical, this point, it says that neither have any idea, the sender's physical layer and receiver's physical layer, what they are sending, is a customer's data or cricket score or what. They only understand the bit that they are sending. They said I am sending 101110. What is that? I do not know. And that is the reason why this thing is called data communication and not information communication. Data is raw data. When you derive meaning out of it, it becomes information. Okay. There are two methods of transmitting. Guided transmission happens in wire. So, the wave travel along the wire's physical shape. In case of wireless, it will just travel in a straight line. Okay. So, it is called unguided. So, there are two different types of transmission, guided and unguided, which is being used. Fiber optic cables use very high frequency, 10 raised to 14 hertz is normally used. While talk about other cables, they use much lesser, much lower value of frequencies. This is using much higher level of frequencies. Anyway, okay. So, duties of physical layer, will begin with the simple thing, converting bits into signals, and the signals are sent across the line and the receiver converts signals into bits. Now, that is the first and the most important requirement of a physical layer, that should be able to do this, but that is not the end. So, there are some issues, like I am sending a data to x and will be received by y, it should not happen. Okay. There may be more than one recipient in line. I am sending something, sending 1, 2, 3, 4. Now, if I am little out of sync, the data that I want to send to 1, I will send it to 2, and then everybody will get wrong data. Okay. 3 distinct problems that we will be talking about. Unaware receiver, I am sending data, but the receiver is not aware, so the data is lost. Speed mismatch, I am sending very fast, receiver is not able to handle the data at that rate, so he is going to drop some packets. Multiple non-synchronized receivers, the very problem that I just talked about, I have multiple receivers and there is no synchronization, I will get some receiver will get data of some other receiver and so on and so forth. Okay. Now, here is a speed mismatch issue. This guy is sending at 2x and the receiver is only capable to handle data at x. Obviously, half of the data is just lost. Okay. Here is the case where you have multiple receivers. I am sending 3 bunches of data, where each receiver will get this thing, and this is basically a device which actually converts this into 3 different paths. Okay. Now, this is the third case, where sender and receiver are out of sync. The sender starts at this point of time and there are multiple senders, S1 to S8 in our case. We have R1 to R7 in this case. In fact, when S1 is sending, R1 should get, S2 is sending, R2 should get, but this cycle starts little early than this cycle. What will happen is, when S1 is sending, there is nobody to receive. So, the unaware receiver, nobody will receive, that data is lost. But when S2 is sending, R1 is listening. So, R1 gets the data for R2, same way R3 gets the data for R2 and so on, nobody gets the right data. Now, this is the other problem. So, physical layer synchronization is very critical. We will not discuss this problem further, because this problem usually occurs in telephone and other communication, will not occur in data transmission, because we do not use such methods in data transmission, but this is also a very critical problem at physical layer. Okay, this is the other problem. I was talking about the duration when I said that, when I was talking about the digital transmission, I said that this duration is very important, and I said that we will look at an example. Here is the example. What is the problem? You can see that here the sender, the time duration is t, receiver's time duration is 1.25. 1.25 times what it is? The result is that sender is sending 1, 2, 3, 4 and 5 ones. What will receiver receive? Receiver receive 1, 2, 3 and 4 ones, just because they are out of sync, and that is a problem, and that will introduce errors. Now, this is critical, and this happens in digital communication, and this is something that we will have to address. And there is actually a more serious problem, because the clocks are so, the amount of data that we send is so fast, even this can happen. I am sending, the sender and receiver's clock are so apart, I am sending 10111101, and what receiver gets is huge amount of data, and it is wrong, all wrong. You may be surprised at this place how it gets 1, because what will actually happen, in the middle the receiver senses the channel and find out if it is plus 5 then 1, minus 5 then 0. So, in the middle it is this, so it is 0, and in this case 1, and in this case the middle is 0. Okay. So, this is how it gets, here also it is so. Point is, I am sending something and receiver gets something else, because our clocks are not synchronized, that is the problem. So, physical layer, because it has to send the bits across and make sure that the bits are received as they are sent, this is to be handled by physical layer. Okay. And one simple way to solve this problem was to send data in this fashion. I am sending 0, I am sending 2 signals, and there is a transition in between. Sending 1, I am sending this signal, there is a transition between. 0 is a higher value before and lower value after that, 1 is lower value before and higher value after that. Okay. So, I am sending 0, 0, 1, 1, 0, and I am sending in every bit you will see a transition in the middle. Okay. What will happen if my receiver has a bigger clock here, this is a little bigger clock? When that is the case, we will expect the transition here little after this thing. When it gets the transition little before, it understands that there is something wrong. So, I will have to like reduce the and it understands the sender's clock is faster than mine, I will have to speed it up, I will have to make sure that my period becomes little lesser. So, it will try, it will do something, but it will reduce, even then it will find that, oh yes, it is taking transition a little before, so I will have to set. But then I cannot escape, as a receiver I cannot escape synchronization, because every bit will have a transition in the middle. As long as my clock is not synchronized, I will find transition little here and there, and I will have to set my clock right. Okay. So, every bit gives me a chance to set my clock right, and I cannot escape from it. So, this is going to have no problem of synchronization. So, this is a great method looking at the requirement in those days. But the downside of this thing is that for every bit that I am sending 2 symbols. Remember the baud rate and the bit rate discussion that we had earlier. So, the baud rate is what? Double than the bit rate. The Manchester encoding was used for Ethernet, first version, 10 MB version. So, 10 MB data that I am sending, I am actually sending 20 MB signals for it, if I use Manchester encoding. So, that is the downside. Okay. The synchronization problem in the solution is discussed here, which I talked about. Here modern clocks are very precise. In fact, Ethernet, the first version of Ethernet, we have not had those great clocks, but today we have excellent clocks available with us, which can take much more precise time duration. Unfortunately, the speed with which the data is being sent is also increasing. For example, if I have 10^10 gigabit Ethernet requires 10^10 ticks per second, 10^10, this is not 10^10 ticks per second. What does that mean? A drift of just 1 upon 100, the 100th part of a second, what will happen? Will wipe out 10^8 bytes, almost 10 megabit of file of moderate size is lost. Even if 2 clocks drift by 1/100th of a second with this speed, will lose an entire file of moderate size. So, that is the problem. Okay. And that is the reason why Ethernet like structures use something called preamble before transmission. A preamble is a sequence of zeros and ones. Now, that is needed here. Why? Because you are sending one, and what preamble is? In fact, it is an 8 byte sequence of zeros and ones. So, what I am doing is, in fact, I am going to do something like this. I am sending 0 1 0 1 0 1 0 1 0 for 8 consecutive bytes. So, 8 into 8 64 bits. I am sending that many bits across. So, we will have almost the same effect as Manchester encoding has. After every byte sent, you have a transition. For example, this is higher. I am not using Manchester encoding now. Assume that I am using +5 and -5. So, what I have is high, low, high, low, high, low, something like that. It continuously varies, and the receiver cannot match. Will understand that my clock is not synced with the sender. Will do that. Okay. So, I will get this 64 bits to do that. So, preamble will help me getting receiver's clock synced with the sender. So, preamble is an excellent solution to this problem. A Manchester encoding is using the synchronization in the signal itself, but it is too expensive, because you need double the bandwidth than the amount of data that you plan to send, which is something which is not acceptable to us. Okay. Okay, I have talked about symbol and baud rate and all that. So, that is being again reminded here. The second critical service that a physical layer should provide is called machine port level addressing. Because you are sending something to more than one receiver, you need to know exactly whom you are targeting. Take the case of this router. Okay. It receives a data to be sent to R3. Now, this interface, this line indicates the interface. So, when R is processing it, will have to give it to this physical layer, then and then will be delivered to R3. Okay. In many cases, it is called an interface. A router will have, in this case, have 4 interfaces. So, here when the packet is being processed and will be given to R3, then it is to be given to this interface. If some other case will be given to some other interface. So, I have 4 interfaces in this particular router, and I need to send it to one of them, depending on who the recipient is. So, the physical layer has to decide. In most of the cases, routers and switches have multiple interfaces which are managed in this fashion. So, the physical layer will contain only one this thing with multiple interfaces like this. Okay. So, that physical layer will have to decide. This is not going to happen in a desktop, because usually you only have one interface and you only have one card which manages that interface. So, that is not the case there, but in case of routers, yes, managing this physical this thing, port level addressing, machine level addressing is very critical. Multiplexing, demultiplexing is the other thing. A fiber optic cable can carry many things together. Okay. So, let me give you an example. Suppose if I am running I am an ISP, internet service provider. I have 5 customers. Okay. Each customer is using a 2 MB line. Okay. What do an ISP need? Multiple lines going out? ISP need only a 10 MB line, only one line, because the customers collective amount of data which is to be transmitted is just 10 MB. And this process is called multiplexing, combining multiple inputs into one single output. Okay. At the other end, the receiving ISP again need to separate it out, and that separation process is known as demultiplexing. So, multiplexing is happening here. Demultiplexing is happening at the receiver's end. Okay. Receiver must separate the signal. In fact, you probably have experienced the same thing in your radio. In your radio, you receive actually a signal which contains all radio stations together, is all multiplex that your radio receives. But when you change the knob, okay, will pick up one particular that thing out of it, and you get it. It is basically, your device is basically a demultiplexing device, and the frequency that you choose is delivered to you. And the other issue is data communication. Now, physical layer has to address this thing. Data communication in physical layer is little more complex, because the data is bursty, and here is an example cases. Let me again choose the board to explain this. Okay. Suppose if this is my client and it types something www.oxforduniversitypress.com. Now, this is here this is the website which I normally do. He is my publisher. So, I communicate with him. So, here is a web server. Now, when I ask for this page, for that particular fraction of a second, my line is completely occupied. But once this page is downloaded, what I will do is I will just browse through that page and look at the books that are available. And what I am going to do is I am going to choose some book to read actually. So, I am browsing that for that period, and here is a very small fraction of time the line is completely occupied, and while I am browsing I am not using that line. And once I choose a book, I again press click on that book, again I experience huge amount of traffic, but after a while again when I chose the book, I am reading the content of the book, I will not be actually using that line. So, the traffic is not continuous, it comes in bursts. The same thing also happens when you use the same network. For example, I am downloading a file from my local server. So, when I say I am using Word to open that file, for example, using the module that I am typing. When I download that, the line is completely occupied, but once I download that doc and I am reading that doc, I am not using that line. Okay. And again once I am completed, I started downloading the other module, or I am changed the content of this and upload it, I am again using that network bandwidth. The point is I am not using this network bandwidth in a continuous form, but in burst, and that is the problem which is described here. And such traffic is bursty, which is very difficult to manage, unlike the continuous traffic. If you have continuous traffic, two simple solutions are used in practice: frequency division multiplexing and time division multiplexing, but that is not going to work, because time division multiplexing you give everybody the same slot, some time. For example, 0 for first 1 second one user will send, second user will send, and so on and so forth. In case of frequency division multiplexing, every user is given a small fraction of frequency in which they will be able to send. Now, neither of them can work here. Here it is explained. Allocated slot, suppose if I am given, I assume that there are 60 users and everybody is given 1 second, and I will get the first second, but then at that point of time my user, the person who is browsing the website, has nothing to access. I am not going to use that time. In fact, in most cases it is so that most cases the user is idle and not doing it. So, if you allocate the time, it is possible that in that time I have nothing to do, and when I am actually interested in sending, I have to wait for 60 seconds to get that, and that may not be enough. So, the same problem is with the frequency. If I am using frequency, I am given some trickle, most of the time I am not using that frequency, and when I want to use that frequency, others are not using that frequency, but then I can't use others frequency and I can't work. So, that is the problem. And that problem, let us try to see that problem in little more detail. Assume that I have 5 users and all 5 users are sending something. So, what I have done is I have divided my available time in 5 different slots. The slot, so slot number 1, sender 1 is sending, slot number 2 this guy is sending, and so on, and slot number 6 again sender 1 will get its turn. When everybody has something to send, like a telephone call, when you are on the call, you are always talking, in fact, you are there, or viewing a video or something. In that case, there is no thing like you are always doing it, like that. It is something which you can always time division or frequency division multiplex, like this. Everybody is using it, and this is the great thing to have. But when you do data communication, the problem is not everybody is ready when there is a time given, or at that frequency, if you use that frequency, nobody is going to use that frequency when there is no data to send or receive. When that happens, the problem is that just assume that I have only one sender, sender number 2 is interested in sending something. In that case, you can see that sender 2 sends his own time slot, and again it appears that he will get one more time slot here and will send. Nobody is sending. So, what the data transmission speed that we have is 1/5 of the actual speed that we can have. So, that is a problem. If otherwise, when 2 has something to send and we do not divide this thing into this thing slots and all that, let 2 transmit, actually 2 can complete this thing in the first this thing for 5 seconds itself. In the earlier case, it needs 5 times more the time. So, that is the problem here. So, this time division multiplexing and frequency division multiplexing is not a good thing for data transmission. Other things are needed and required, and we will be looking at those things later in later modules. But before we embark on that, we will need to have an introduction to something called electromagnetic spectrum. So, whenever we are using some frequency, we are using frequency from this electromagnetic spectrum, and electromagnetic spectrum starts from frequency 0 to infinite. In fact, that is what it is. Then would like to look at what that is and why that is useful. In the next module, we will be actually throwing more light on this, but here we will have some introduction, the basic idea about this thing. Okay. So, we have already seen, okay, there is something called wavelength. Wavelength is the length of the wave. Okay. Frequency is number of times it oscillates. We have already seen that is just a repetition of that. The frequency increase or is like this. Let me give you an example. Okay, this is my wave and it oscillates twice in a given time. So, what is the frequency? Frequency is 2. Now, if I increase the frequency, it will oscillate 3 times in a second, 1, 2 and 3. Okay. The wave is reduced, you can see that. So, wavelength is reduced. Point is, when you increase frequency, wavelength is reduced. Okay. So, here is an example. So, the wavelength, okay, this is smaller amplitude, the wavelength is the distance or this, okay, the same. So, when you talk about the electromagnetic spectrum, the radio range is this 10⁴ to 10⁸. 10⁸ to 10⁸ is called microwave. This thing is called infrared. This is visible light, that is we only can see this, nothing else, or hear this. Ultraviolet is this, X-ray is that, and above 10⁻22 is called gamma rays. The last two ranges are not used for data transmission for obvious reasons, because it is hazardous to human beings. So, that they are not used, but the rest is used. I must tell you one thing, that these ranges that I have written here is just one representation of it. You go to any website, you will get different values. Okay. So, these ranges do not make much of a sense. In fact, there is no fixed area which these ranges define. But anyway, you can look at this thing from some other aspect. That lower end part of the frequency is called radio waves, higher end part is infrared and UV, including visible light, and the middle part is called microwave. All three of them are used for transmission, and we will be looking at what are the characteristics of the wave which belong to this radio part, the characteristics of the wave which belong to this microwave part, and the characteristics of the wave which belong to the infrared and this visible light and UV part, and how they are deployed to get the job done. Okay. So, with that note, we will conclude this module. In this module, we have seen complete we concluded with the electromagnetic spectrum, but before that we looked at how transmission takes place. Okay. The physical layer, we actually began with physical layer and what the transmission and the issues of synchronization and related things we have seen. Okay. We have also seen that the frequency division multiplexing and time division multiplexing in their raw form is not possible to be used for data communication, because the data transmission is bursty. With that note, I would like to conclude. Thank you all.